Okay, good afternoon, everyone, and welcome to this second iteration of a whole series that we are going to have with in collaboration with Qualcomm. This is essentially about topics in computer science, electronics, essentially anything that can be related to basic systems, right? So the whole idea of this ongoing seminar is to train students, or at least give them an idea of whatever is going on currently in the systems world. Today, we are really happy to have Sushim with us. Sushim, I'm just going to, even though he was with us last time as well, so some of you have probably already, met him, talked to him. But I'm just going to give a very brief introduction so that we can, get started in the formal fashion. So Sushim started his career as a 3G protocol stack engineer, moving forward to take on different roles like chipset software lead. He then continued to work on 4G and 5G connectivity, multimedia and application processor software. He has been working in the wireless semiconductor industry for almost 22 years for now. And out of that, 17 years have been as a part of a Qualcomm. For the past 5 years, he has been particularly working on compilers, cloud computing, machine learning, and software security. He has been and hopes to remain passionate about computer science ecosystem on a global scale. So without really, taking much of his time, we are going to start this session. I'm going to just hand over the podium to Sushim. Sushim, over to you.
Thank you. Thanks a lot, Professor Saurabh, and thanks a lot, Professor Abhishek, for giving us an opportunity to talk at IITISM. We are very happy to be here, and speaking here is definitely very important for us to develop computer systems ecosystem in India and globally. So today's talk or today's session is we are concentrating on a very basic level that why should somebody pursue compiler design? What is the end product when people see? Because what happens is when students look at products, how does compiler design is enabling this product, or how this end product is happening due to the work in compiler engineering? So this is what we are trying to connect, and we have kept this talk at without prerequisite level, and we'll follow up again with specific compiler optimizations. And again, that talk also doesn't require a prerequisite of knowing compiler design. So we'll get started. So yeah. So here I'm trying to build a base. This was again in the last session also, this was spoken about, that mobile smartphones are an amazing technical achievement. And if you look at it, the capabilities of smartphones are mind-boggling right now. Why I'm taking my smartphone as an example to build a case is because I understand smartphones more, but the similar cases for compiler design will go for compute, IoT, and any kind of compute devices, smaller or bigger. So if you see the mind-blowing performance, in case like the current smartphones, performance numbers are better than 1990 supercomputers, early 2000s servers. I still remember when I started my career in 2000, my PC was 1/10 of the current CPU clock of a smartphone. So that's how far we have come. Then high quality multimedia. I will just take one example. China National Geographic magazine used a smartphone to record 8K Ultra HD video, not those complex cameras. So we have come to that level in multimedia capabilities. Location-based navigation, most of us are using for directions. We are looking at 7.5 Gbps data rate, and internet connectivity anywhere, and the long battery life. So what a 60-watt bulb at your home consumes in 15 minutes, in same power your mobile phone runs for 24 hours. Now let's talk about 1995 and 2020. So in 1995, it was 500 nanometer process, uh, and now we have moved to 7 nanometer process by the Moore's law. Moore's law is more uh, an observation than a law, but since it has stood for so long, they consider mm, it as a law. What Moore's law states as that every 2.5 years, the number of transistors on the same area will double. So if you look at that 1.4 million transistors in 1995, and now more than, this is 2020 again, now it is much more than 10 billion transistors in 2020. CDMA voice only in 1995, 7.5 Gbps 5G modem now in 2020. 2.84 gigahertz octa-core CPU, GNS location service, 5 cameras, 8K video encode decode, Xbox One class GPU, and computer vision and AI acceleration engines. So uh, all these things have come, you know, at a lot of work from the whole engineering world. And one of the most important thing I will talk about is, this is like, when you see all those capabilities, so though there is a one chipset you see, but inside one chipset there are many processors, many DSPs, many hardware accelerators. So there is the computer architecture inside the chipsets are of the varied quality and the varied instruction sets. So while these devices have become complex, what has happened is there are more and more uh, uh, varied architectures have come, uh, computer architectures with different instruction sets. And because of those different instruction sets, when you are writing an optimized program, you need to know the different instruction sets on different architectures. So this has been a big challenge. I'll explain you why in a little while. Moore's law is also slowing down. We are close to 5 nanometer in transistor size. I don't know how small we can go down. Software has always not improved as fast as hardware has, but now software will have to uh, play a larger role. Can't rely on only hardware improvements. As I spoke about earlier, that there are a lot of hardware blocks augmenting the main CPU for, let's say, image processing, ML applications. An explosion of these different hardware accelerators have made the developer's job difficult. Let me explain you here. Like, let's take computer vision or image processing as a domain. That domain itself requires so much of knowledge, and there's such a deep domain. Now, people understanding both image processing and underlying architecture and writing optimized code for underlying architecture is too much of ask. Code will be non-portable because there is another chipset and you have to write an optimized code for another chipset using that chipset instruction set or that architecture instruction set. You will have to again learn a new architecture, and you already have to be expert in computer architecture, sorry, in image processing, and you have to learn the computer architecture of different underlying processors, and then you have to write an optimized code for underlying processor. Why optimized code is important, I will tell you a story right here. When I started my career, there were my friends who were working on the non-embedded side and on the on PC side and on the server side, and at that time there was not so much of heavy application on the server side. So the embedded side people will be very worried about battery power consumption or the power consumption, because we have to last on a battery. So they will say, oh, don't worry, we have a power connection. But off late you would have been heard in news or you would have read about it that even in these cloud servers which are kept in the different locations, the heating has become a problem. So now having an optimized code running on underlying architecture is extremely important. Also, in case of embedded devices, there are more constraints. like there might be some very small CPUs, very constrained CPUs for IoT, industrial IoT, and they will have very low memory. From there to supercomputers, all these are computers, and the same program need to work efficiently across different architectures. And security obviously has become bigger and bigger concern. So we cannot really rely on only hardware to solve these problems and technological progress. So here we'll talk about how compilers comes to rescue. Let's again talk about the image processing case, because I have taken image processing and machine learning as example, because most of the students nowadays relate to, or it is easier to relate to image processing, the camera, camcorders, and machine learning. Everybody knows about it. How compilers are enabling image processing and machine learning. So compilers are abstracting hardware complexity. So now let's say you are a machine learning expert. So you focus on machine learning. There are or you focus on image processing. You're image processing expert, and use a domain specific language, and then compiler team will take care of generating optimized code for underlying architecture. So so in this case, uh, let's say if your underlying target architecture is a DSP or a CPU or or an accelerator, the compiler team will take care of generating optimized code for that underlying architecture. Another very important part is compiler optimizations can help you in reducing the code size for memory constrained architectures. Uh, Also, you would have already seen when you are doing projects, even for your student projects, a lot of libraries, a lot of code is already existent and is legacy. So similarly in industry also, 80 to 85% code will be legacy, and you'll be writing a new piece of code which will be to for a newer application. So when this legacy code, which is maybe 5 years, 10 years, 20 years back, was written for that underlying architecture, it is not optimized for the new instruction sets or the new architecture on which it is being ported to. So compiler team takes care of that too. They will write optimization in such a way that the legacy code also run in an optimized manner on the newer architecture. It takes care of the newer instructions and the newer capability of the newer architecture. So uh, and many a times what happens is there might be a hardware limitation. Like we have seen a scenario, it was discussed last year CGO conference also, that a very small microcontroller was not able to do out of order execution, and compiler took care of it by using superblock scheduler, which will be talked in or spoken about in the next talk. So those hardware limitation can be worked around using compiler design. Code becomes portable, easy to test, debug, and profile if with a good compiler. Now, this was all, talk. Now we will get into exact examples. So I will take you through two examples, one of image processing and one of machine learning, how compiler design is enabling that camera or those camcorders and all those things. So first, I'll take you through a little bit of image processing, uh, couple of minutes, which only that part which is related to today's context, and then we'll move forward. So yeah, as I said, I'll take you through domain specific language, one for image processing and one for machine learning. Let's get started. So Halide is our image processing example, which we'll talk about it. Halide is a domain specific language for image processing and computational photography. So fast image processing pipelines are difficult to write uh, because there are different different stages of the pipeline, and we have to optimize the pipeline in by vectorization, multi-threading, tiling, etc. Traditional languages like C++ make expression of parallelism, tiling, and other optimizations very difficult. In Halide enables rapid authoring and evaluation of optimized pipeline by separating algorithm and the schedule. I'll talk about what is algorithm and what is schedule in the next slide. Front end of a Halide is in C++. So if you have a traditional legacy code written in C++, you can embed your new Halide code in that and it will compile fine with it. So here I'm taking a small code example in Halide where we are doing a horizontal blur. Horizontal blur is nothing but average of 3 pixels on the x-axis. So if you look at the code below, you will see fxy, the line there, and let me get a pointer. So if you see here, the fxy equal to input. So this is the algorithm, what you are doing at that pixel. Like you are averaging 3 pixels on x-axis, and this will not change. This is algorithm is what we are doing. And schedule is how the computation will be organized or how you will access the pixel which is processed. So the schedule is what defines the performance of program. Okay, so you are able to I think grasp this part, like algorithm, like what we do at pixel, and how the computation will be organized at the pixel is the schedule. And this is how the program is clearly separated. Once you have finalized the algorithm, you need not change the algorithm because that is fixed. For performance, you'll play around with the schedule to get a better performance. Are you able to see the animation?
Yes, we can.
Yes. Okay. So the blue boxes represent memory read and yellow boxes represent memory write. So in every image processing pipeline, whatever the last stage gives you output is a producer for the next stage, and the next stage when it is processing it, it is called as consumer. So if you look here, we are producing the producer first and then consuming it. Can anyone tell performance wise what's wrong here? Anyone? Why there will be a performance problem here? Okay, I'll go ahead with that one. So let's say the producer is fully produced and then consumer is starting reading it and or processing it. So by the time we are at the end, the initial part of producer will be evicted out of cache, and we will be we'll be fetching it from memory, usually much slower. So in this case, this is a poor cache locality. So I'm trying to introduce concept of tiling here in image processing. So let's say we look at now here in this case, for better cache locality, rather than whole image, we are producing a tile, we are consuming that tile, producing the next tile and consuming the next tile, and so on and so forth. So this will get us better cache locality. So performance of program by doing tiling is getting better for image processing, better cache utilization. Now what we can do more is we can go with tiling, vectorization, and parallelization all together. So here, if you see, we are processing it in 4 threads, tiles, and 128 pixels together. That is vectorization. So this program will be much faster. So I have quickly introduced a concept of tiling, vectorization, and parallelization so that we are able to, understand how this is helping us. So let's look at.
There is some comment, Sushim. So it says, so Nikhil has said that context switch will be more as after some time again, process has to bring in the cache memory. I think he's trying to answer the question that you asked before.
Yes.
Right.
Okay.
Okay,
Sure.
Nikhil. Yeah, you're right. But
You're
yeah,
right. Yeah. So let's get to the, now I'll first prove the point why domain specific languages, and then it will be implied how compiler team is helping it. So if you look at the comparison of algorithms, both in Halide and C++, more or less similar, not very complex, but for complex algorithms, it can be tough, but that is not the point. Algorithm is pretty okay if we are writing Halide versus C++. Let's look at scheduling part. So we are doing here tiling and loop unrolling. So loop unrolling, there is sometimes trade-off between the code size and performance, because with the loop unrolling we avoid branching, so performance gets better. But in there will be slight code bloat, so that will be optimization. People will take care of it. Optimization engineers in the background. So here, if you see for just tiling and unrolling, I'm comparing code between C++ and Halide. So it is pretty simple. So if you have to play around with the code, play around with the different values, it will be much easier in Halide when you are trying to optimize the performance. And if you want to do vectorize, not possible in C++ without an auto vectorizer. Now this is when I'm comparing it with C++, but when you are writing optimized code for embedded devices, some of the DSPs, sometimes you will have to use the intrinsic instructions for that particular DSP or underlying architecture or underlying micro architecture, or you might have to use assembly even, which will get the two code comparison very, very complex. So here's summary about Halide. Halide program consists of two major components, algorithm and schedule. The separation between algorithm and schedule is key. It enables, once you logged your algorithm, you need not change it. And the schedule you can quickly change and experiment with it and get a highly optimized result. And your compiler team will take care of writing an compiler for targeted architecture so that the optimized code is generated for your Halide. So let's look at this piece. This piece talks about a 3x3 convolution written in Halide on the left-hand side and written in HVX intrinsics on the right-hand side. So if you look at it on left-hand side, it's very simple code. If you have to change or play around with any of those values to get better performance, you can quickly play around with it. While on the right-hand side code, it requires you to understand first the underlying DSP architecture, then write the code in intrinsics. And if you have to do any optimizations and all, you will have to really work hard and the code will not be maintainable. Also, another thing, you are an image processing. Here in the case is image processing. You are an image processing engineer. Your expertise is image processing. So will you keep understanding different underlying architectures and writing optimized code for it, or leave it for underlying compiler? And one big question which always comes is, handwritten code always will be better optimized than a high level language. You can look at it, both are pretty comparable. 0.114 cycles per pixel, and Halide is slightly better with 0.109 cycles per pixel. So both pieces of code are very, very comparable. And on the left hand side, you could play more and more with this piece of code to get optimizations quickly. It is easier to play with the schedule on the left hand side of Halide code. While we look at the right side code, this code is written by people who understand the architecture. Imagine the performance what you would have been gotten on the right hand side if in HBX intrinsics, if you don't understand the architecture fully. So Halide version, 14 lines of code, and on HVX interface, you can see this much plus 94 more lines. Very concise, easy to maintain. Developer can quickly restructure schedule to optimize an algorithm. So it is very, very fast. The coding process, the productivity of programmers is very good using Halide. So advantages of using Halide versus intrinsic or assembly. Development time and cost. Of course, the Halide program you can write much faster. Expertise, when you are using assembly or intrinsics, you need to understand the underlying architecture, scales to very few programmers, and how many underlying architectures you will learn and write your code for it. Uh, Even for let's leave that part. Let's look at the same DSP for you have written the code. If the new version of DSP comes up with new instruction set, you will have to rewrite or change certain part of the earlier written code. While in case of Halide, the compiler team will take care of the new instruction set, and there will be no problem at all. Assembly and intrinsic programming does not scale to very large code bases. Understanding is tough. There will be automatic optimization, which will be like, again enabled by the compiler team. Halide allows programmers to easily tune for program for performance. Like you can play with the schedule very quickly. With Halide, there is no change in code required for the newer versions of DSP. Here, Hexagon DSP of Qualcomm we are talking about. Compiler will automatically take advantage of new hardware features and instruction set. So while we were speaking about this, one of the conferences in China, we were always talking about that how good it is to program in Halide, how fast it is and all. So one of the persons, very senior person, had an objection saying the handwritten code always be better, and then it is very what you are saying, will it stand when can you really show it to us? So they asked us to write, if I remember correctly, it was a box filter. So we coded box filter very quickly in very short time. They had already written code optimized for Hexagon DSP, which was performing in 6 milliseconds. Our Halide code, which we wrote, came 30 plus milliseconds. I believe it was 37 or 36, the first iteration. Within 20-25 minutes, we could iterate over that code, iterate over that schedule again and again, changing values, and we could hit 7 milliseconds within 25 minutes. So how quickly or how faster you can optimize in Halide or a domain specific language it is that simple. But will you be able to do same for a code written in assembly? May not be. You can focus on your expertise, which is image processing, and leave the compiler team to do optimization for the target architecture. Also, I'll give you another example how it has enabled my other part, that you focus on image processing and leave optimization to underlying architecture. There was a company in Germany. These are material engineers and not computer engineers. And they wanted to write a piece of code which will run on Hexagon DSP, which will differentiate between the different materials like wood, rubber, plastic, and all those things. So they used Halide, and compiler took care of all the optimization, and their code ran fantastically optimized on underlying architecture. So see, this is enablement. It was not required for them to understand underlying architecture, what is the instruction set is to write optimized code. And this was a big enablement. Material science engineers writing image processing code, and then it is working fine on an underlying architecture. Another popular example of Halide's success was Google Pixel 1. If you heard, they talked about Halide in their press release, and the best camera ever had. So that camera was enabled by a camera pipeline which was running on Hexagon DSP enabled by Halide. So a lot of optimization work went on by compiler engineers to get that best camera ever ad running on all the radios. So this is about Halide, my first example, how compiler engineering has, or compiler design has enabled image processing. Next, I will take example of machine learning. I will go faster on it and leave a longer time for Q&A, because it is primarily based on similarly like Halide, TVM. So it's an end-to-end compiler stack, supports multiple hardware targets. There is a wide industry adoption already across Amazon, Huawei, Intel, ARM, Alibaba, Nvidia, Facebook, and many, many more. Because Halide example has proved a point on domain-specific languages. So this was easier adoption. So we have added support for Qualcomm Hexagon DSP Hexagon vector extensions to TVM, optimized for HVX hardware features. Just to one more point I wanted to mention here. Any of you want to use Halide or TVM, you don't need the real hardware to run it. You can download Qualcomm Hexagon DSP simulator, and you can run your programs written in Halide or TVM on Qualcomm Hexagon DSP simulator. It will give you accurate results as it running on a real DSP. So same thing for TVM also and Halide. Code is written in Python, which more or less people are aware about it. So the first question will come from the audience is Python is not optimized for embedded systems. So here in this case from Python, an intermediate representation is generated using TVM and LLVM, and then it is an executable which is compiled for underlying architecture. It is not an interpreted code. So here compilers build the Qualcomm Hexagon DSP binaries from Python code with some additional directives like .tile or .vectorize or .unroll, which we saw in Halide. The same applies to TVM also. This makes TVM code portable. It can run on different Hexagon DSP versions, the same code. Even if there is a compiler team which is on a different microarchitecture or different accelerator or different DSP, they have written code to optimize it for that DSP. The same TVM code will run on a different hardware also. You will not have to write an optimized code for another underlying architecture for your machine learning ops. So yeah, TVM supports both Hexagon DSP simulator and Hexagon DSP hardware, as I spoke earlier. And this works very well for HVX, given the nuances of the ISA. Confirmed for Halide experience. Halide, we have already done this, so we are more confident about doing TVM. TVM we did after Halide. So use cases. So focus is on providing ability to author ML ops. Like, most of the ML engineers will not be conversant with the intrinsics of or the assembly programming of different DSPs or different microarchitecture or different hardware accelerators. So here they can write ML ops in Python, and it will work fine. Compiler team will take care of generating optimized code for underlying architecture. Hand authoring of ML ops for underlying architecture is expensive because it will require intricate knowledge of underlying DSP architecture and micro architecture. It does not scale. It does not scale. You cannot ask an ML or a deep learning engineer to learn different underlying architectures and write optimized code for different underlying architectures. TVM will enable customers to author ML ops and plug into Qualcomm ML workflow, as I talked about in the last slide. On our simulator, you can use our hardware to do it. And with TVM, you can program Qualcomm DSP without understanding the intricacies or the instruction set of Qualcomm DSP. TVM also supports scalar non-HVX code generation, so it will be transparent to you if you use TVM to do machine learning. It has a simple programming model. Again, from Halide experience, we have seen algorithm and schedule separated is a very good model to write code, and programmers can author custom op using Python. TVM compiler compiles Python op to Hexagon DSP, and TVM generated op is integrated into Qualcomm's ML workflow. User can run their ML model using generated custom op. And I'm very sure that there will be other companies also who will be enabling TVM for their architecture too. So using TVM for machine learning is easier for you. You need not understand underlying architecture to write optimized code for underlying architecture. Getting to the example here, if you look at TVM code for quantized element addition on the left hand side and right side, you can see the hand authored assembly, 25 lines of Python versus 601 lines of assembly. You can already see which code is maintainable and which is not, which you can play with, schedule easily and optimized. Enable the Qualcomm hexagon programming for all. No expertise in the processor internals needed. You need not learn the underlying instruction set to write optimized code. So again, compiler team will enable machine learning engineers to write machine learning optimized code without understanding the underlying architecture. So till here, we talked about two domain specific languages or framework, which enables image processing and machine learning. Uh, and I have, built enough case about how compiler is enabling it. And I talked about consistently compiler optimization, compiler optimization, compiler optimization. So in next talk, we will speak about 3 optimizations. Again, no prerequisite required. You need not know compiler design to understand those optimizations, so that you are able to appreciate if compiler design is your cup of tea. Do you want to really work in this domain? Another good thing is LLVM compiler is an open source compiler. So from student life, if you want, you can contribute to the open source, you can upstream your code, and your code being used by community, everyone who is using LLVM compiler, is a great sense of achievement. Here I will digress a little bit and get into program analysis, because LLVM compiler also provides static analysis tool. That why static analysis is important, and because this is one of the fields where you can contribute a lot. Being an open source, you can write different checkers. Program analysis is a very, very good field. I'll give you an example. There was a rocket series, and they have launched already the 4 rockets in that rocket series. And before launching the 5th in the series, they saw a static analysis warning. And they ignored, since we have already launched 4 and nothing happened, nothing will happen in 5th also. And 5th rocket was launched in that series, and within 8 seconds, the rocket went into flames, because that particular code, it was, I think it was a overflow of a variable, was hit in that particular scenario. Because warnings are always not happen in every scenario. I have another case where I remember, and the rocket went into flames. $300 million went into flames within 8 seconds. I'm not talking about, this is just bill of materials of the rocket. I'm not talking about the effort put in by all the engineers and the time spent by all the engineers. So there is ignoring it was very costly for them. There's another example which I'll bring why it did not hit in the first 4 rockets. I have seen in my career one of the crashes where what happened is there was an array index which was uninitialized, and code was only crashing when that uninitialized array index was initializing to a negative value. Otherwise, it was not crashing. So not every time that garbage value will not be negative. So it was not crashing every time. The code was not crashing every time. So this is a case which I built for static analysis. And you can look at the dollar value analysis of when a bug is caught at what stage and how much is the cost to fix it. Look at this. If, let's take the case of Qualcomm. If a Qualcomm device is launched and a bug is found by somebody, this is the bounty which we pay per bug. Let's do a dollar value analysis of static analysis using LLVM security tools. Let's say when at development time we caught a bug, so 10 hours bug fixing time, $54 per hour engineering cost, so $550 is the cost to fix the bug. Let's say when the device is already launched and bug is reported externally, the cost includes bounty payments, huge engineering effort. Like now the device is already in the market, fixing the bug, propagation to all the branches, all the devices which are already launched. And of course, if somebody finds that bug, they will call a press conference, talk about it, and reputation damage to the company, which we cannot put a dollar cost on it, but it's a cost to the company. Cost of fixing these bugs in production after the devices are launched, engineering expense per bug, let's say 10x. So $550 at the time of development, $5,500 per bug. Average bounty payout per bug, $7,500. So even if it catches, static analysis catches 20 bugs, which is a very small number, it catches in hundreds and thousands. So $260,000 plus reputation cost it will save if LLVM static analysis is used. So if you want, for example, in automotive world, which is a very new, you can write checkers for automotives, which are like MISRA is the standard, ISO 26262 and ASIL are the automotive safety standards. So if software checker which are not existent in LLVM SA, you can write that checker upstream into LLVM, which will be used by the world, and you can do smaller projects. There can be very simple checkers, there can be complex checkers, and you can choose and do. So there are multiple checkers which are not available in LLVM static analysis now. You can go ahead and enhance LLVM static analysis while and learn program analysis. That's another important stream like compiler design. So summary of the presentation. Hardware diversification poses a lot of challenges, difficult to port new use cases to different hardwares. There are low memory and the low power CPUs. Security is major concern. Need efficient tools and tool chain to overcome these challenges to keep the pace of rapid technological advances. And LLVM compiler is one of such tool. With this, I will open it for Q&A. If you have any questions about presentation, about career in compiler design, you can ask me the question. If you want to reach out to us for internship or career opportunities in compiler design, you can, I will just put this slide, the first one where our email ID is there. Ravi leads compiler design team, who will be speaking on the next topic of optimizations. He will speak about 3 optimizations, and anyone can understand who has not even taken the compiler design course. So you can reach out to us on our email for any career opportunities or any questions. Like I have had a few of the students speaking to me about I want to work in compiler design, but I want to do my PhD also. So is it or is it good to go after PhD just after BTech, or I should work in the industry? So for it will depend on case to case. So but you can speak to me about those things also. Your professors are there who are much more knowledgeable than me on that topic. You can speak to them and you can reach out to us. So here are our email IDs. We are open for question and answers.
Thank you, Sushim. Any questions from the audience? You have a lot of things to, I'm pretty sure you have a lot of things to ponder over, but we can probably take a few questions right now. There is some question in the chat.
Yeah. One I have gotten here. So to what extent portability affects compiler design, optimization, and other issues? Okay. So we definitely, when Qualcomm's compiler design team is designing, we will definitely keep in mind that the program is portable across Qualcomm DSPs and Qualcomm whatever CPU we are using and different version of DSPs. We may not keep in focus that across other companies DSPs, so there is portability consideration while we are doing it. And in optimization, the primary consideration depends from which spectrum of architecture we are using. For example, your higher end phones, they have enough memories. You will see nowadays, I don't know, 8 GB, I think 16 GB RAM is also there. So memory constraints and is other memories also, there is not a problem on high end. So their code size optimization are not that important, but on those chips we work a lot on performance optimization. Like there were cases where we got more than in higher double digit performance benefit by compiler optimization in camera preview, for example, by compiler optimization. When we come to low end chips like some of the IoT chips where power consumption is very important, memory are very small, there even the memory optimizations are very important, and there is a trade-off then again between memory and performance. So yeah, these optimizations on from case by case basis, uh, there is trade-off, and we work on compiler team works on looking at underlying architecture, how it is, um, how the underlying architecture is, and what will be optimal to do, like whether memory optimize memory versus performance trade-off, what is the optimal point.
Any other questions? Okay, so one question that I had in my mind is that the compiler teams that are working on this, it's certainly a very challenging task to produce optimized code for any DSL. The point is, from what I see, that like how difficult it is for a compiler guy, because as you said, right, that let's say there is some change in the underlying architecture, right? It could be, let us say, a newer version of the architecture comes up. So now you made a very good point that let us say I am an image processing expert. For me, learning 3 different architectures is very difficult, right? But let us say we'll have a dedicated team for all of these different architectures, a dedicated compiler team. My question is, like, how different is it, let us say, when you get a new version of an architecture? Like, for example, I'm working on certain architecture, I'm in the compiler team, then a new version of the architecture comes in. Like, what is the amount of time it takes to switch over, let us say, so you'll have to learn new skills, right? As a compiler expert, you'll have to learn new skills in order to make the current code more optimized towards the current architecture.
Okay, yes, very good question here, because so you're saying the same problem is there with the compiler engineer, what is there with the image processing engineer, right? Because if new architecture comes in, the compiler engineer needs to understand the new architecture. So essentially it is a domain kind of difference there. This is a definition, probably, compiler engineer, we use word compiler engineer, but over the time he or she evolves as a systems engineer, where though the compiler is the center of it, they need to know computer architecture, because high performance computer architecture, because when they are generating a code for a architecture, they need to understand that architecture, not in as detail as a computer architecture engineer, but that knowledge is required. Advanced OS and principle of programming languages, so all these concepts come together, and a compiler engineer over a while evolves as a computer systems engineers, having expertise in compiler and knowledge of most of the domains of computer systems, including program analysis. How complex it is? Yes, when a new architecture, the first version of architecture is evolving, it is complex. But when from one version to next version, the things get easier because the changes are incremental. Also, then what happens is uh, over the time when they have gained expertise over that architecture, even not from version to version, for same version, they try to find more optimizations and more optimized execution. So the quest for optimization doesn't stop even if the version doesn't change. So they are in a constant quest of optimizing the generated code, uh, whether version changes or not. But yeah, first version or first new architecture has a bigger problem, or a lot of work from compiler team. But from version to version of a hardware, it starts getting easier for us.
Thanks, Sushim. Yeah, any other interactions? So Sushim has already given his contact details on the slide, as he has already mentioned. If you would like to interact with him or Ravi, so Ravi, I think, is going to be our next speaker.
Yeah,
So
yeah,
as you guys can already see where this is going, we are moving into a more deeper understanding towards systems, right? And
yeah,
so we started off with a very basic talk last time. It became slightly more focused this time, and next time we are hoping that we'll deep dive into compilers a little more, especially with the optimization stuff.
sure.
So if there are no more questions, I would like to thank Sushim. Any last questions? Or
I will send across the material to Professor Saurabh, and he can share with participants. Even I will share, like, for absolutely beginner, how they can start in compiler and quickly ramp up and start, and how then you can deep dive later. So I'll send that note also to Professor Saurabh.
just thank you. So because we have some second year students here as well, and I've already told them that this is a very good chance for them to, because they are just starting off right now,
Yes,
and maybe they probably did not understand much in the talk. I could see that some of them joined and then left. Probably they were not really getting too much of the knowledge. But one thing is for sure is that if we can point them to certain resources to start off with,
sure.
then they are probably in a good shape. They'll be able to within the next 2 semesters or so, they'll be in a good shape to even, let us say, apply for an internship at Qualcomm. So,
I'm even of a different thought. My thought is, even they don't pursue compiler design, they should know what different domains are available, because there will be something which will be rage, and every few years it changes, right? It's now like AI ML is rage. So people are blindly picking up a domain. My thought here is, try compiler design. You like, it's good, you can pursue. If you're not, you have tried, and move on to try something else, not just blindly following what everyone else is doing.
right. Right, that is actually a very important observation by him. So I think that would be it from our side today. This was a very nice second iteration of this talk, and I hope that at least those people who were there with us from the beginning, they enjoyed it, and we just hope that this interaction continues. Next time we'll have
Sure,
Ravi with us, and he'll be
sure,
talking about a little more detailed optimization related perspective.
sure,
So thank you, Sushim. Thank you, Qualcomm,
sure,
for engaging with us, and thank you everyone who joined us. We'll be meeting again probably in 2 weeks of time.
sure.
Thank you.
Okay.
Bye,
Bye.
everyone.
Bye.